Hi, today I'm going to walk you through my analysis of the closest pair of points algorithm by using divide and conquer techniques. And we will explore why the naive approach is not efficient and how geometric insights lead to optimization and how the algorithm extend to 3D dimensions. And for the first part A, is ask to solve this recurrence using back substitution. So we are given the recurrence t of n equals 2t of n over 2 plus n squared over 4 plus c. So first we can expand this by using t of n over 2 equals 2t of n over 4 plus n squared over 16 plus c, and t of n over 4 equals 2t of n over 8 plus n squared over 64 plus c. By using back substitution to solve this, we can see that t of n equals to 4t of n over 4 plus 2 times n squared over 16 plus 2c plus n squared over 4 plus c, and equals to 4t of n over 4 plus 3 times n squared over 8 plus 3c, and also equals to 8t of n over 8 plus 7 times n squared over 16 plus 7c. So after k level of recursion, where n equals 2 to the k, and we have t of n equals 2 to the k times t of 1 plus the summation from I equals 0 to k minus 1 of 2 to the I times n over 2 to the I quantity squared over 4 plus the summation of from I equals 0 to k minus 1 of 2 to I times c. So when n over 2 to the k equals 1, where k equals log base 2 of n, the summation from I equals 0 to k minus 1 of 2 to the I times n over 2 to the I quantity squared over 4 equals the summation from I equals 0 to k minus 1 of n squared over 4 times 1 over 2 to the I, which equals to n squared over 4 times the summation from I equals 2 to k minus 1 of 1 over 2 to the I. So it's approximately n squared over 2, n squared over 4 times 2, which equals n squared over 2. And the summation from I equals 0 to k minus 1 of 2 to the I times c equals c times open parenthesis 2 to the k minus 1 close parenthesis, which equals to c times open parenthesis n minus 1 close parenthesis. So after k levels, where k is log base 2 of n, we got t of n equals n times t of 1 plus our geometric series that sums to n squared over 2 plus c times n minus 1. So this simplifies because each term is half the previous one, giving us the factor of 2. Therefore, the result we get is n of n equals to theta of n squared. So when we use master method to verify this, we have that t of n equal at of n over b plus fn, where a is 2, b is 2, and Fn equals to 2n squared over 4 plus c. As Fm equals n squared over 4 grows faster than n to the 1, we use case 3, and we can get t of n equals theta of n squared. Therefore, both methods yield the same result. For part B, it asks that for each point P in the strip, only the next 7 points in increasing y order are examined. First, why is this sufficient? Actually, the geometric packing insight in statement 510 can explain that only the next 7 points in the strip sufficient. At most 8 points, including point P, can lie and or on the 2 delta times delta rectangle centered at any point in the strip. The 2 delta times delta region is divided into 8 delta over 2 times delta over 2 squares, and each square can contain at most one point that maintains the minimum distance delta constraint. Suppose 2 points lie in the same square. The distance will be at most delta over 2 times the square root 2 less than delta, which is not the definition of delta as a minimum distance. So checking the next 6 points is enough in y-sorted order. And the second question is SS. Could it be that all 7 points lie on the side as P? The answer is yes. According to the statement 5.9, there is 6 Q and Q and R for which the distance between Q and R is less than delta. If and only if there exists S and S prime belongs to the strip S, such that the distance between Q and S and S prime is less than delta. Therefore, the algorithm doesn't need the points on the opposite sides. It only checks if any 2 points with the strip S are within the distance delta. These 2 points S and S prime might both from Q or from R, or one on each side. So the strip contains points with distance delta of dividing line L from both left and right halves. It's okay. For the third question, explain why this doesn't affect correctness or asymptotic performance. For the correctness part, according to the statement 5.9, there exists Q in Q and R for which the distance between Q and R is less than delta if and only if there exists S and S prime and strip S for which the distance between S and S prime is less than delta. This states any cross-defined pair closer than delta must in the strip S with 2 delta. Also, in the statement 510, by checking each point in its next 15 neighbors in SY, we check every possible pair that could be distance that less than delta. The algorithm checks all such pairs, no matter the points are in the same side or opposite side of dividing line L. As the algorithm doesn't miss any closer pair, the correctness is guaranteed. The symplectic performance O of n log n doesn't affect because each point checks at most 15 other points, so the time processed the strip is O of n, and the recurrence is T of n equal to T of n over 2 plus O of n, which substitute T of n equals O of n log n. RC, it asks us that does the closest pair algorithm rely on the assumption that all x coordinates and y coordinates are distinct? Yes, it does, and this can cause some problems. And what challenges might arise if some coordinates are repeated? If there are x coordinate duplicates, it may affect recursive splitting and strip definition. Since the divide and conquer algorithm splits the points by x coordinates into left half Q and right half R, it will be unclear to split points to left and right if the points with identical x coordinate. Also, if some points have duplicate x-coordinate near dividing by L, some points may not be included or will miss them. And B, what precautions or tie-breaking strategies can be applied to ensure correctness and preserve all of n log n complexity? In order to ensure correctness and preserve all of n log n complexity, we can use sorting with tie-breaking. Sort by xy, primary sort x coordinate, second sort y coordinate. If x is equal, use y to break the tie. Also sort by yx, primary sort y coordinate, second sort x coordinate. This strategy ensures consistent ordering. Also, we can decide where to assign points with identical x coordinate as the dividing line when partitioning. And for part D, outline how the closed pair of points algorithm extend to 3D, and how do you recursive calls and strip-based merging generalize when the closest pair of points algorithm extended to 3D. First, just like in 2D, we split points based on x-coordinate into two halves and recursively solve the left and right halves to find the closest pair in each half, and the strip becomes a slab with two delta centered around the dividing plane. In the merge step, the strip contains all points with distance delta, and we all check the nearby points by merging. And what new geometric considerations arise? In 3D, points now have x, y, z coordinates, and instead of dividing line in 2D, we have a dividing plane to divide point set. A step is used in 3D, which is a rectangle prism. And C, is all of n log n still achievable? Yes, all of n log n is still achievable because the recursive division is the same to split into halves in each step. In merge step, we still have all of n to pursue the 3D step as we only compare each point to a constant number of nearby points, so the recurrence is still t of n equal to t of n log n over 2 plus all of n, and it solves to t of n equals all of n log n. And that's it. Thank you.